Here we have a normal distribution. As you can see, a normal distribution gives us a bell-shaped curve, which is perfectly symmetrical. So what we have on the left is exactly what we have on the right. Okay. Here we have again the normal distribution. So here we have the scale. So imagine that we are talking about IQ points, so intelligence quotient. And as you can see here, the mean for the IQ for the population is 100 points. And we have a standard deviation of 15 points. So this is why we have here 115, that would be 1 standard deviation, 130, that would be 2 standard deviations, 85 would be -1 standard deviation, and then 70 would be -2 standard deviations. Underneath here you have another curve, and this is what we call the standard normal distribution. Now, why is this called the standard normal distribution? Notice what we have done. Originally we had a mean of 100. Now we have transformed that mean of 100 into a mean of 0. Okay, so my original mean was 100. When I convert it into the normal standard distribution, it becomes a mean of 0. Here we had 15 units for the standard deviation, so 115 was my first standard deviation. So here we have 1 standard deviation. Notice that 1 standard deviation becomes a 1 in my normal standard distribution, my normal standard curve. 130 was 2 standard deviations, that becomes 2 in the normal standard distribution. 85, we said that was -1 standard deviations, so that becomes -1, and 70 becomes -2, and so on. Okay, so when we convert the normal distribution into a standard normal distribution, what we are doing is we are making the mean of the normal distribution, we are converting that into 0 in the normal standard distribution. And each standard deviation here, so here in this case was 15 points, that was 1 standard deviation, it becomes 1 unit in the standard deviation. Now, why is this nice? Well, let's imagine, for example, that you have a score of 115 and you want to see where you are in comparison to the rest of the population. Okay, so let me move the cursor here to 115. It's a little tricky to get that there, but we got it. Okay, so there we have it in 115. So notice here then that here we are in 115 and we want to see what areas we have here. So here we can see that on the left we have 84.09%. So that means that if you have a score of 115, you're at the top 85% of the population. For the same token then, notice that that would also mean that you are within the top 15.91% of the most intelligent people. Okay, so here we define 2 areas then. So we have an area to the left, so that gives you your the top 84%, and then here you would be among the top 15.9%. Okay, so this is also one advantage of the standard normal distribution. The standard normal distribution then allows us to see percentages that we have. Imagine that you have a score of 130. So let's move this to 130. Let's see, 128. Oh, I went over 129.8, 129.8, 129.9, 130. Hope I didn't go over. Okay, there we are. So here you have 130. So then that means then that you are on the top 97.7%, and that also means that you're among the 2.28% of the most intelligent people if you have a score, an IQ of 130. Okay, so the normal standard distribution allows us to see, to compare you with the rest of the population, where you are in terms of the population. Imagine that we decide that we want a 95% confidence interval, and then we want to see how much data we have between -1 and 1. Okay, so I am going to now go to two tails. Okay, and I am going to put my cursor here in 1 -1. Okay, there we go. So we have it, 992, 993, 994. I went over a little bit. Okay, here we are. Oof, it's hard to I keep on going over. All right, there we go. So we can see then that this is what we call the central limit theory, that here in the center, if we have between -1 standard deviation and 1 standard deviation, we have approximately 68.27%. So in terms of the data, that's also what we would have. We would have about 68.27% of the data. What if we moved to 2 standard deviations? So let's go to 2 standard deviations, and we want the distance between 2 and 2 standard deviations, just a little bit more. Okay, so here we go 1, 2, 3. Oh, still too high. Okay, almost there. Okay, 2 standard deviations. Let's see. So we have 213. Okay, 207, almost there. 205. Still 205. Okay, 203. Okay, 1, 2, 3. Okay, there we go. So between -2 standard deviations and 2 standard deviations, notice that now we have an area here of 95.45%. So that would mean that we have about 95.45% of the data in that area. And then if we did 3 standard deviations, so let's do 3 standard deviations here. Okay, so we have 3, almost 3. Okay, almost 3. Okay, 3. Okay, 3. There we go, 3. Then notice that now we have 99.7% of the data here, and then we have 0.0013 or 0.13% outside. Okay, so notice that also this allows us to see how much data we have in between the area. So if it's between -1 and 1, we have approximately 68%. Between -2 and 2 is 95%, and -3 and 3, that's 99% of the data, approximately. Okay, so that's another advantage of the standard normal distribution. Finally, with the standard normal distribution, and this is going to become very important when we do testing, hypothesis testing, normally we're going to define a confidence interval. Okay, so in this case, normally the confidence interval is 95%. So I want a 95% in the middle there. Okay, so here we have 99. Okay, so here I have 94. So I want a 95% in the middle there. 94, I went over. Okay, so 95.23, 95.24. Okay, let me move from here then. So we want a 95% in the middle there. Okay, so we have 90. Oh, there we go. I went over. Okay, here I went over a little bit. Okay, so I have 95.04, 94, 99, come on, 95. It's very hard. Okay, here we go, 95%. Also, this point here, notice that it's not quite -2. It's a little bit before -2 and before 2 here. And that point is exactly 196, minus 196 plus 196. This is what we call, in this case, the critical value. Okay, so this is also going to help us define the critical value. And then when we run a test, that test is going to give us a z value or a t value. We're going to be talking about the t curve later. Then we will decide whether we are in the white area here, and in that case we would not reject the null hypothesis. But if we fall within the blue area, then notice that we would reject the null hypothesis. Okay, so those are the advantages that we have when we work with the normal standard distribution curve. So the first one is that because it defines areas, and the area is exactly 1 under the curve, we can determine percentages. So we can see whether we are on what top percent of the population, or we are among the best other top. Then we can also define what percentage of population we have between the different standard populations. And we saw then that between -1 and 1 we have about 68 point something percent. Between -2 and 2 we have about 95 and something percent. And then between -3 and 3 we have about 99.7% of the data in that case. Finally, the third point then was that it also allowed us to define here a certain confidence interval, and in this case 95% is the typical interval, and it also defines here a critical value, and in this case is -196 or +196. And with this then we can define two areas against which we're going to compare the result of our tests. So if our result falls within this white area, then we would not reject the null hypothesis, but if we fall within the blue area here, we would reject the null hypothesis. Normally, we use the normal standard distribution, sometimes also called the z-curve, when we know the population standard deviation. But in language acquisition in particular, and in most experiments, we do not know the standard deviation for the population. So in that case, we have to use a t-curve. Now I'm going to add a t-curve on this graph. That would be a t-curve. Now when we compare a t-curve with a z-curve, notice that we have two main differences. One, the t-curve, the red curve here, is flatter. Okay, so we will compare, it is flatter, and is also fatter on the sides. Okay, so notice that a t-curve compared with the z-curve is flatter at the top and fatter on the sides. Now notice what happens when I start increasing my degrees of freedom. So here I had 1 degree of freedom, now I have 2, 4, 7, 9, 10. You see, the more degrees of freedom I have, the more the two curves become alike. 13, let me go all the way to 30, so to see what happens when we get to about 30. When we get to about 30, the two curves are more or less the same, pretty much the same. There we have 30. So you can see here the two curves become pretty much the same. Okay, so using a t-distribution is going to be very important when we have fewer points of data. So if we have fewer than 30, a t-curve is what we would need to use. But if we have more than 30, then we can use the z or the t. Typically, people use the t-curve all the time, so to play safe. So remember then that the two curves become pretty much alike when we have about 30 degrees of freedom. In other words, when we have 31 pieces of data. Now, the same way that we did this, let's make 20 degrees of freedom now. Okay, so I'm going to bring my curve down to 20 degrees of freedom, and I'm going to have only a t-curve. Okay, so this is my t-curve with 20 degrees of freedom. I can also then find areas here. So everything under the curve is going to be 1. And then I can distinguish areas. So for example, if I have here, I'm going to put 2 tails, and I am going to try to define 95% in the middle. Okay, so let's go and see if we can get it 95% in the middle. So here we have 99 point something. There we have 0.96. Okay, so let's try to reduce that. I'm going to try to get 95. So here I have 95.24, a little bit more. There we go. 99. Okay, one more. That should be 95. 95. Okay, so now I am in 95. Notice that now that I am in 95, again, I am not exactly in 2 standard deviations here. I'm now a little over 2 standard deviations. Remember when we did this with the z-curve? In the z-curve, the value was a little bit before 2. Here's a little bit after 2. And as you can see in this case, the critical value now is going to be 2.08. Okay, so if I have 20 degrees of freedom, in other words, if I have 21 pieces of data, notice that I am going to have then a critical value of 2.086. Okay, and again, that's going to be the point against which I'm going to be measuring my results. If my score, my t-test, falls within the white area, then I do not reject the null hypothesis. But if I fall in the red area here, then I would reject the null hypothesis. Okay, so the same way that with the z-curve we found a critical z value, now we can find a critical t value. And then if we are in this area here, in the 95%, then we do not reject the null hypothesis. But if we fall in the red areas here on the sides, then we would reject the null hypothesis.